Yes, sir. You're live now, sir.
Oh, thank you. Hello, everyone. Good afternoon. So, this is Balakrishna, okay, on this live session. Uh, those who have already joined, I have written in the chat box. Please write your name and the college in which you are studying, and also what course you are studying in the chat box, so that I know about you people. Okay. And also, if you have any question, you can start. So I'm going to take one more live session in the third week of March. Okay. If you have any question, collect them and then keep them handy. And once, okay, the in email comes about the second live session, immediately put your questions so that I can answer in more detail to clear your doubts. Those who have joined already, okay, please write your name once again and tell from which college and what you are studying. Hi, Aish. So you are studying in Mysore. So how you found it helpful in your course, Interpretative spectroscopy? So in your studies, are you using any spectroscopic instruments like IR, NMR, mass? Of course, M pharma, B pharma. Okay, the spectroscopic techniques are very, very essential to look into the purity of um, precursors and end products. So, what are the instruments you have in your college in Mysore, Aish? Nice. So, you have any question about NMR? Good. Okay. So this course is helping you in your studies? So those who are already in the session, please write your name and tell from which college you are and what you are studying quickly. Please start writing. I do not know where Panth is. No. And knowing about Panth is beyond the scope of this course, I think. Right? So don't ask these questions. Ask any question that is pertinent with interpretative spectroscopy. Okay. I'm not here to tell who are my friends and all those things. Ask some questions relevant to interpretive molecular spectroscopy course. So others may not be interested in your questions. Hey, Shefali, you have any question? For MSc students who are planning to take CSIR, this is a very, very useful course. So course material for fifth week will be shared soon, don't worry. Why does CDCl3 gives the triplet in 13C NMR? Okay, when you look into 13C NMR of CDCl3, okay, so C is bound to D. So if you look into D, I equals 1. Okay, if you go for 2Ni plus 1 rule, okay, so here 2, 1 into 1 plus 1 equals 3. That means carbon 13C, when you look into it, this is coupled to D. Okay, Di equals 1. So according to 2Ni plus 1, it will be 3 lines. And here, okay, intensity will be equal. It comes around 76.1, okay, because of 13C coupled with deuterium. Okay, so it gives a triplet. So 14N nucleus at 6 Tesla, magnetic field is, okay, dash. Okay, that already answer is given. Okay, how? Okay, you can compare. Okay, gyromagnetic ratio is given, and 10, what is that? 110. Okay, what is 10 7? 10 raised to 7 Tesla per Tesla per second. Okay, gyromagnetic ratio. So the equation is, black equation is there. From that one, you should be able to find out, right? So everything is given. 14N, okay, 6, okay. Magnetic field is given, okay. Gyromagnetic ratio is given. You know the equation, right? You should be able to find out that. Why intensity 1 is to 1 is to 1? Yes, it is 1 is to 1 is to 1. Uh, so what happens is, if you take 13C, one, this nucleus, it can interact with the D. So 3 is this one, right? See, this is alpha, say beta. If it is there, what you can have is, yeah, you cannot have any different one. So one will be like one will be like this, one will be like this, one will be like this. All are equal opportunities are there. So here in all these cases it interacts. So all possibilities are 1, 1, 1. Okay, so plus 1, minus 1, and 0. So as a result, what happens? You will see all are 1 is to 1 is to 1. For example, if you go for spin half, basically what happens? Let us say alpha, alpha. Okay, so then what would happen is alpha, beta, okay, beta, alpha, and beta, beta. It is something like this, it comes. Whereas in this case, there is no such scope, only one is there. So these are all three are interacting equally. So as a result, what would happen is intensity is 1:1:1. And also you can also go for Pascal triangle. In Pascal triangle, of course, you should remember uh, Pascal triangles will be different for different I values. I equals half, you have a different Pascal triangle. I equals 1, you have a different Pascal triangle. And I equals 3 by 2, you will be having a different Pascal triangle. And all these Pascal triangles already have given in my lecture. Okay, how to calculate. Even for CDCl3, when I equals 1, how to calculate also I have given. Just you can look into it. Okay, what you should do is listen to uh, lecture carefully and also look into the problems and then find few more problems in textbooks and try to solve them so that you can have proficiency in the interpretation of spectroscopic data. Yeah. Okay. Tungsten complex. Yes. In case of tungsten complex, okay, so that tungsten has two isotopes, right? Uh, One of the tungsten isotope is about 5.4%. Okay. So even if you do not know, let me take another. Yeah. So let's assume, let's not worry about now the tungsten. I will tell you. So it is tungsten. When you look into tungsten, it is 183 tungsten. So NMR active, it I equals half, and it is 14.3% abundance. Okay, so let us see one phosphorus is coupled to tungsten. Let's not worry about what else is there in it. So in this case, what happens when you look into 31P NMR for a metal complex containing phosphorus as well as tungsten, you should remember uh, 183 tungsten is NMR active is 14.3%. Other one is about 785.7. Okay, it is NMR active, I equals 0. So that means if I take a complex like this, 100 molecules of this one, out of 100 molecules, approximately 14 molecules will have NMR active tungsten, and remaining 85 or 86% do not have okay, NMR inactive complex. In that case, what happens? We have to divide the NMR spectrum into two components. One with NMR active tungsten and another one without NMR active tungsten. In that case, what happens? Let us consider first this one without NMR active. In that case, that you get a that you get a straight line. You get one line like this. So now, okay, remaining 14% of the molecules, 14 molecules would interact with tungsten, 183 tungsten that has I equals half. So here that will split into doublet. Again, you go for 2Ni plus 1 rule. Okay, so here 2 into number of tungsten atoms is 1 and spin is half plus 1. So it becomes 2. That means you get a doublet. So then you will get a doublet here. Doublet is equally disposed to the central one. This also chemical shift for this one here, I equals 0. And this one is equidistance from this one. Okay, it's a doublet. And this will be having, let us say this will be intensity is 85.7 and this will be 7.2 and 7.2%. Okay, intensity. And these are all called satellite peaks. And this distance will tell you J, 1J, PW, okay, coupling constant, and this can be anywhere between 120 to 240 hertz. Okay, depending upon what other ligands are there and all those things. So this is how you can see, okay, interpret 31 PNMR of a metal complex having tungsten bound to the phosphorus. So you will see, okay, a triplet is not a triplet, a singlet, okay, for bulk of the molecules which have I equals 0 tungsten, and then the 14.3% that will be having two peaks doublet, equidistance from the middle one, and this is the chemical shift. This is the chemical shift, and then this is what you call the separation that is called the 1J phosphorus to tungsten coupling. So that comes around 120 to 240 hertz, depending upon the type of phosphines, type of phosphorus atoms we have. That means different kind of substituents and also what kind of ligands we have on tungsten, other ligands. Okay. So these peaks essentially when the peak intensity is when one nucleus is interacting with less abundant. Okay, we come across satellite peaks. These satellite peaks are quite common in case of 77 selenium coupling, okay, 29 silicon coupling, and 195 platinum coupling, etc. Okay, is that clear for you? Is it clear? Shefali, is it clear? So similarly, you can also explain, okay, a platinum complex where there is a bond between phosphorus and platinum. If you take enriched, okay, tungsten, for example, if you take 100% 183 tungsten, in that case, you don't see satellites. You will get only two doublets. Okay. Not the pattern I showed you. It's only when you have both of them. Okay. So natural tungsten, where we have only 14.3% of 183 tungsten. So any other question? What are hapticities? Okay. The hapticity we talk about uh, metal complexes bound to so one bond and two bond coupling. Yes. See, usually when the two atoms which are coupled go farther and farther, the coupling becomes weaker. So always one bond coupling will be stronger, two bond coupling will be weaker. It goes like that. If the two nuclei which are separated by more than one bond, okay, then they go with that one. If they are separated by one bond, we call 1J coupling. If they are separated by two bonds, then 2J coupling. If they are separated by three bonds, we call 3J coupling. For example, you take so something like this. Okay, so if it is coupled to this hydrogen, this is 2 bond coupling pH. And if there is one H is there, this is 1H 1J pH coupling. And if it is coupled to this one, then it's 3J pH coupling. And if it is coupled to this one, it is called 4J coupling. So this is how the coupling goes. So when the coupling partner goes farther and farther, the coupling also becomes weaker. So that means basically farther bonds have the magnitude of coupling will be very small. Is it visible now? So in YouTube, it takes a while. Okay. It is not synchronized. It comes much later.
Sir, you double click the entire screen, sir, for his.
Okay. It's visible now.
No, sir.
Okay. Let me share it again. Is it visible now?
No, sir. Yes, sir.
Huh?
Yes, sir. Now
Yeah.
it's coming.
Okay. Can you see now the share? Yeah. Okay. Yeah. So any other question? Is it clear for you now, the couplings? Is it clear? Is it clear, Shafali, now? Oh, okay. Okay, you are asking about hapticity. So hapticity arises when we talk about the coordination of, olefins, okay, or organic compounds, cyclic organic compounds having more than one double bond. For example, if you take benzene, it has three double bonds are there. Let's say if only one double bond is bound to uh, metal, then it's called eta 1. And if two are there, then it's eta 2. And if it is three, it is eta 3. This is how it goes like that. See, for example, if you take cyclopentadiene, okay, So this is, it is called eta 5. So the eta 5 means it makes bond to all five, okay, atoms, all five carbon atoms. Okay, so then it is eta 5. Okay, if benzene is there, if all the bonds, all the three are making, okay, so then it becomes eta 6. Okay, so then become eta 6 means 2, it binds like this to the metal. This is called eta 6. Okay, this hapticity indicates the how many bonds are establishing bond to the central atom. Okay, so sometimes what happens, these having multiple double bonds, they have the, they can coordinate with one double bond, two double bonds, or three double bonds, be, depending upon the requirement by metal to satisfy 8 electron rule, if there is a provision. Okay, so for example, if you take this one here, minus, okay, let's say something like this. And if it simply binds here, it is eta 1. Okay, and then if this binds here, 1, 2, 3, then it becomes eta 3. Then this two binds, it becomes eta 5. So there are examples of cyclopentadienyl anion showing eta 1, eta 3, eta 5. Or sometimes what happens, it can also delocalize something like this. Okay, so it depends. Okay, we can take a specific examples to see. A hapticity refers to the number of bonds established by a cyclic system to the organic cyclic system to the metal. So that indicates hapticity. Hapticity will give you a clear idea about the nature of the bonding between the organic molecule to the metal. Is that clear? So someone asked me about hapticity. Of course, this hapticity also we can identify using 1H NMR. Okay, for example, if eta 5 binding is there for a metal, then what happens? It will show only one single resonance for the entire C5H5 anion. On the other hand, if it shows only here, then it will show for one H here, and then it will show only one for this one, other two different. On the other hand, if it is two are binding, then unsymmetry is there. It will show four different peaks. Okay, so the hapticity information can also be extracted from 1H NMR. And simple electron count based on what kind of other ligands we have, we can also try to explain that one. Is it necessary for an organic cyclic system to show the maximum hapticity or intermediate one? So that depends how much knowledge you have about electron counting and organometallic chemistry. Ayush, can you see the screen now? So any other questions? Okay, one bond and two bond coupling. Okay, I will take an example, specific example to explain you once again. Can you see the screen now? Can you see the blank sheet so that I can start writing? Ayush? Can you see the molecule I have written? Okay. So now you see here, phosphorus is there and hydrogen, this is one bond apart. So this, if one H is interacting with phosphorus, okay, this, and if I'm looking into the phosphorus NMR, let us not worry about these groups here, organic groups here. Let's focus about this one. And if I see phosphorus is one bond apart from hydrogen, and if I see phosphorus NMR, it will show a doublet. And this spacing is called 1J pH. So this is 1J pH coupling, some value, okay, 200 hertz or whatever, okay, okay. So now forget about this one. Now I have here two hydrogens. And if it is coupled to these two hydrogens, then it will be a triplet. So then if you just look into this one, 1, 2, okay, this is two bond coupling. This is called 2J pH coupling, okay, some value. And if I consider here, this is 1, 2, 3 bond coupling. This is 3J pH. Okay, so this is what, okay, this is how you can explain one bond coupling, two bond coupling, and three bond coupling. Is it clear for you? If I take something like this, and here this is one phosphorus, this is trivalent, and this is pentavalent now. Okay, so now this phosphorus, if I take phosphorus NMR, we have two different type of phosphorus centers here. One is trivalent, one is pentavalent. They have a totally different chemical shifts. And this one, if I say put X and this is Y, okay, or this if I call this A and this is X. So if I look into delta A, this will be a doublet and delta X will be a doublet. And this doublet is due to two bond PP. This is two bond coupling. Okay, this is 2J PP coupling. And here also 2J PP coupling. If this is coupled to this one, the magnitude will be same as this coupling to this one. So this spacing will be identical. Okay. So that you can write two chemical shifts, but only one coupling constant. Both are identical. So this is how you can explain. And if there is a bond like this, okay, and then if it is something, if they're both are different, then here also you will see coupling. This is 1J coupling. Okay, this will show a doublet, this will show a doublet. Okay, but this is 1J P coupling. Here also 1J PP coupling. So this is how you can distinguish 1J, 2J coupling. Is that clear for you? Is it clear, Ayush? 1J coupling means two nuclei which are interacting are one bond apart. Two bond coupling means those nuclei which are interacting are two bonds apart. 3J coupling means they are three bonds apart. Okay. So the 2, 3, all these numerals, whatever we are using, that gives information about how farther they are, how related to each other, or how far and what are the how many bonds are between them is described by this terminology 2J, 3J, 4J. You can see sometime in in special cases up to seven bond coupling. Up to seven bond coupling you can see in special cases. And for this communication of these two nuclei, what happens? Electrons will facilitate. The electrons in between will facilitate through which they will interact. And if there is a continuity of electrons are there, then coupling will be there. If there is a node is there, then the communication is cut off. As a result, in some cases, you may not see any coupling. Okay, if you have a nodal region between two NMR active nuclei, in that case, what happens? You may not see coupling because the communication is cut off. It's almost like having a valley, okay, in between. So one river is there, one atom is this side, another an atom is other side, and there's no communication. If the bridge is there, they communicate. The bridge will be here electrons. Is that clear? If more s electrons are there, coupling will be much stronger because s electrons are much close to the nuclei. Okay, so wherever we talk about coupling, okay, so coupling essentially occurs because of the s electrons, okay, facilitating the interaction of two nuclei. If S character is more, coupling will be more. If S character is less, coupling will be less. Okay. For example, in some cases, when you go for Bend's rule and all those things, if you look into the sp3 hybridization and other things, if S character is less, in that case, the coupling will also be 2J coupling will be less. If the S character is more between the two nuclei, NMR acting nuclei, then the coupling will be varying. So you can verify some of these things when you get an opportunity to look into molecules. Is that clear? So any other question? So you collect all your questions, okay? Send it to me in advance. Okay, as I said, March 3rd week, I'm taking another live session. Before that, okay, please send those questions, okay, so that I can come up with more examples and all those things keep ready. So that helps. Okay, so thank you then. Okay, see you all in my next session. I wish you all the best. If the exams are there before, do well and spend more time reading textbooks and solving problems. Yeah, thank you all for joining. See you next month in the next live session.
Yes, sir. Session is stopped, sir.
Oh, okay, good.